Hello everyone. In this chapter, we are going to talk about wind and the desert. We will learn about the global wind patterns. Where do deserts develop on Earth? And what are the controlling factors to develop a desert? What are the depositional processes in deserts? The global wind patterns are developed due to a combination of differential heating from the solar radiation and the rotation of the Earth. The following videos will show you how the global wind patterns are developed.
The sun is our main source of heat. This heat travels to us through space in the form of radiation. This radiation is absorbed by clouds, atmospheric gases, and by the Earth's surface. Some parts of the Earth receive more of this radiation than others. The main reason for this is the curvature of the Earth. This curvature means that at higher latitudes, the radiation from the sun is spread over a much larger surface area, while the same amount of energy is much more concentrated near the equator. The radiation also travels through a greater depth of atmosphere nearer the poles in comparison to the equator, so more radiation is lost to scattering and absorption by gases and particles in the atmosphere. The tilt of the Earth also means that polar regions do not see daylight during the winter. Here the Earth is continuously sending out heat to space without any compensating incoming heat from the sun. These cold polar regions are where we see lots of snow and ice. Snow and ice, and also thick cloud, reflect a lot of the sun's radiation back into space. The reflectivity, or albedo, of the underlying surface is an important factor in determining how much of the sun's radiation is used for heating the Earth. The combined effect of all of these processes sets up a thermal gradient between the equator and the poles. In fact, the global radiation balance is such that poleward to 40 degrees latitude, the outgoing heat radiation from the Earth exceeds the incoming heat radiation from the sun. Global circulation acts as a clever air conditioning system, redistributing the heat, stopping the equator becoming hotter and hotter and the poles becoming colder and colder. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves, before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the feral cells. Unlike the other cells, the feral cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created, so these areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms, giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert. With more precipitation falling in the Sahara, Antarctica is the largest and driest desert overall. The spin of the Earth induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. This is the Coriolis effect. The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection. As the atmosphere rotates with the Earth, it is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and has moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere. How does this lead to eastwards flowing jet streams and prevailing winds? As air moves away from the equator at the top of the Hadley cells towards higher latitudes, it starts to be deflected by the Coriolis force. Just as a skater spins faster by bringing their arms and legs closer to their bodies, air moving away from the equator speeds up as it gets closer to the Earth's spin axis. This process is known as the conservation of angular momentum. The magnitude of the Coriolis force increases towards the poles, so by the time the air reaches 30 to 40 degrees north or south, it is moving in an eastward direction. This subtropical jet stream occurs high in the atmosphere between 12 to 15 kilometers. It is associated with some of the strongest winds on Earth, reaching over 280 miles per hour at times. As this jet sits between the descending branches of the Hadley and Ferrel cells, there is little associated weather. The polar front jet forms in a different way. This jet sits between the rising branches of the polar and Ferrel cells. It marks the boundary between cold polar air and warm tropical air, known as the polar front. The polar front jet occurs at a height of 11 to 13 kilometers and is primarily the result of the temperature contrast across the polar front. The stronger the temperature contrast across the front, the stronger the jet. So it follows that the polar front jet is stronger in the winter than the summer. Waves or ripples along the jet stream can cause Atlantic depressions to deepen explosively as they are steered towards the UK. Winds at the surface are also subject to deflection from the Coriolis force. The surface flow of the Hadley cells form the persistent trade winds. As air flows towards the equator, it is deflected towards the west in both hemispheres, forming the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The persistence of these winds allowed sailing ships to cross the Atlantic and opened up trade routes between Europe and America, giving them their name. The surface wind in the Ferrel cells would flow from a southerly direction in the northern hemisphere, but the Coriolis effect causes this wind to be deflected to the right, leading to the prevailing westerly and southwesterly winds often experienced over the UK. This setup is not unique to our planet. Jupiter also has circulation cells similar to those on Earth. A day on Jupiter lasts for about 9.5 hours, so it is rotating much more quickly than the Earth. The great size and fast rotation of this planet makes the Coriolis effect very strong. This splits the Jovian atmosphere into many circulation cells in each hemisphere, producing numerous alternating bands of rising and falling air and giving Jupiter a distinctly striped appearance.
Besides the solar radiation and the rotation of the Earth, the continental distribution influences the global wind patterns as well. So the global wind patterns are not three perfect circulation cells on both the northern and the southern hemisphere. The complicated wind patterns determine the global climate patterns on Earth. Anywhere on Earth receives less than 25 cm per year precipitation, it is considered a very dry area, and the desert can develop in those areas. Globally, deserts are developed near the south and the north 30 degrees latitude, and in the polar regions as well. The southern and the northern 30 degrees latitude are places where hardly sail, and the mid-latitude sail brings warm, dry air, descend the air from high altitude to low altitude. The descending of dry air do not promote precipitations, so those areas are very dry. The polar regions are very cold, and the cold air has very low capacity of moisture, so the polar regions are very dry too. However, if you look at the global desert distribution map, the polar regions, the north and the south 30 degrees latitude, are not the only areas that have deserts. For example, the western U.S. has deserts across large variations of latitudes. So the same to the South America and the northwestern China. They all have deserts that developed way beyond the north and the south 30 degree latitudes. This is telling us that the global wind patterns and the climate controls are not the only factors that influence the development of deserts. Tectonics is another factor influencing the development of the desert. So, evaporated water from the ocean contains a lot of moisture. If it climbs up against a mountain, will produce rain. After rain, the air parcel becomes dry. Once the air parcel crosses the peak, it will descend fast on the lee side of the mountain due to gravity. This descending dry air does not provide precipitation on the lee side of the mountain. So on the lee side of the mountain is very dry and becomes a desert. This is the case for the western U.S., where the Rocky Mountain blocks most of the moisture from the Pacific. It is also the case in the South America, where the Andes block the moisture from the Pacific. And the same to the northwestern China, where Himalaya and the Tibetan Plateau block moistures from the Indian Ocean to the continental interior of China. Other than tectonics, climate change will influence the development of deserts too. Global warming will increase the aridification of the continent. And as a continent getting dry, more deserts will develop. More deserts means more dust in the atmosphere. When the dust deposits on top of glaciers, it decreases the albedo of glaciers, which makes the glacier absorb more solar radiation and melts faster. This will further increase the global warming effect and accelerate the warming. In addition, human agricultural development also increased the aridification of the continent, and the developmental activities have changed the climate system and enhanced the aridification. Now let's talk about how sediments that are transported by wind, which is the primary process of deposition in the desert. Wind has a limited transportation capacity compared to that of the river. Wind can only transport the dust and the sand-sized sediments. Sand can be transported for a relatively short distance, which means that it cannot be transported to another continent across the sea. The motion of the sand transportation is a combination of rolling and hopping. In the picture to the right, it shows that sediment transportation velocity is increasing with the fluid velocity increases, which is the wind speed increase. Similar to the river deposit, when wind is slowing down, the larger particle-sized sediment will be deposited first, and eventually the silt and clay-sized particles will be deposited to the last. It is also the reason why dust can be transported for a very long distance across oceans to another continent. Here are some examples of dust transportation. Wind is also a very good media for erosion. Sediment transported by wind will become better sorted and better rounded the longer distance it is transported. Where there are gravels and pebbles deposited on the surface in the desert, the sand and clay-sized particle will be eroded away through time, left the gravels and pebbles on the surface, which forms the desert pavement. Sand dunes deposit is the dominant desert deposition. During transportation, the sand grains will be physically weathered, so the grain size will become smaller and smaller during transportation, and the roundness of the grains will be better rounded. Because the wind transportation capacity is limited, and only certain size of the grain size can be transported, the sediments deposited by wind are also well sorted. So the wind velocity on an uneven surface is not constant. When the wind is blowing against a slope, the wind velocity is fast on the surface. After passing the crest of the topography, the wind velocity decreases on the surface. So when the wind velocity is fast, sand grains are eroded and transported over the crest of the topography, where on the lee side of the topography, wind velocity decreases and the sediment will be deposited. This is how a sand dune is formed and how sand dune migrated. Morphology of the sand dunes are controlled by wind directions in the area. Where there is only one dominated wind direction, sand dunes in straight, sinuous, and Barchan forms are common. When the wind direction changes through different seasons, more complicated sand dunes can be formed, such as star dunes. In the desert, sand dunes are not the only deposition. There are also rivers in the desert, because in the desert there is a minimum vegetation cover, Once precipitation happens, within a short period of time, flash floods can happen to the area, and braided rivers can be formed quickly to serve as the runoff channels for the rainwater. This river can transport a lot of sediments in a short period of time, and because the groundwater table in the desert is very low, soon enough this river will infiltrate into the ground and contribute to the groundwater. Before the flash flooding, braided rivers contributing to the groundwater, lakes in the desert can be filled by this river. This lake may or may not disappear after the rain, but the size of the lake will fluctuate a lot during and after the rain. In the dry climate settings, the lakes in the desert will be charged by the rainwater. The lakes will also be dried out soon after the rain. These type of lakes will produce deposits of evaporite minerals. Here are some pictures of a typical desert evaporite deposit from Texas. Okay, so that's all about wind transportation and the desert deposit. See you next time.